All right, good morning, everyone. Today we're going to finish up on limits of definite or limit definition of area. We started a practice problem that we didn't get to finish, so we'll finish up with that. I didn't get a chance to go over trapezoid rule, so we'll definitely spend the majority of our time going over trapezoid rule. And I do want to review the topics that we've covered in these past 3 days, but we have plenty of time next week, I feel, to do that. Our quiz is not until next Friday, so I want us to go over some of the problems that I didn't get to chance to go through in the packet next week. After I go over limit definition of area and trapezoid rule, we're going to move on to see if we can get introduced with integrals, with power rule for integrals. We'll try to finish everything up by all the new material up by Monday. Okay. And we can start quiz review on Tuesday. We have 3 days for quiz review. Quiz is not until next Friday. Okay. Hopefully you guys are trying to keep up with each of the homework assignments. I'm not going to check these homework assignments until next Wednesday. Okay, but I think it's good if you're trying to keep up, so you're not trying to wait until last minute to do all the homework assignments. Also, I have 2 packets for you when you come back to class on Monday. Many of you guys have printed out the notes that we've done these past couple days, but I'll have a packet with some additional problems and worksheets. It's also the packet that you see at the top of the chapter 4 page, but I'll go ahead and print one out for you as well. And I also have a packet for you for 4.1 and the quiz reviews when you come in on Monday. So let's start off with finishing up that limit definition of area problem that we started yesterday at end of class. So we talked about how with limit definition of area, we're just trying to insert the pieces that is provided in the problem to begin with, and then working towards getting this height component out of function notation. All right, so here's our function, 2x squared minus 3x plus 2. Bounds are provided as 1 and 3. That's our a and b value. So the first thing we need to do is to establish that width. So the width is b minus a over n, 3 minus 1 over n, which is 2 over n. We're holding on to n because we don't want to just be stuck with 2 or 4 or 8 rectangles. We want to push that n out to infinity, but that's not going to happen until the very end. So we're going to hold on to n variable until the very end. Okay, we start making our substitutions here. B minus a over n can be replaced with 2 over n. Our a value is 1, so 1 plus 2 over n times I. So now we can see that we have a width component and a height component, but the work that we need to do is to get this height component out of function notation. We know that this is the argument for the function, but this is not the expression that we're using, right? These are not compatible here. So we're going to be have to involve this original function somehow, because this original function in the problem is going to highlight the heights of each of the rectangles. So here are the steps that I want us to take. We're going to rewrite it as a function as f of x. F of x equals 2x squared minus 3x plus 2. Spend the time to rewrite the function with spaces reserved for the argument. So the way you do that is every time you see an x, just go ahead and create a parentheses where that x is. Everywhere the x is, go ahead and set a parentheses in place of it. That way you have a clearly reserved place where the argument is going to go. Okay, if you have it, and if you're able to show the step, I feel like you're going to have a much easier time avoiding issues with knowing where to put that argument. Okay, so now that you have all those parentheses showing, fill in those parentheses with the arguments that you see here. So everywhere you see a parentheses, you're just going to put 1 plus 2 over ni. Now we can start making our substitution, right? This high component can now be replaced with this 2 parentheses squared minus 3 parentheses plus 2. That goes here. Okay, with component, high component, everything is now self-contained. We don't have to bring anything else in. Now we're just going to be working with this expression, trying to get this all cleaned up so that we can eventually work in our summation formulas. And once everything's in terms of n, we can do limit as n approaches infinity. So now our parentheses squared. First thing is I want to try to resolve the parts that we can focus on first, which is this binomial squared. So I'm going to write this binomial out twice. Make sure that you're cleaning this up in the correct way, right? In the correct order. That we're not distributing the 2 through, that we're not distributing the exponent through. We're taking the time to FOIL this out, and then we can distribute the 2 through. Okay, so we don't always go from left to right. We want to do order of operations, exponents, parentheses, take precedence before any multiplication. Okay, so we square this binomial here. We get 1 plus 4 over ni. I skipped a step here. I added the middle terms here. 2 over ni plus 2 over ni gives me 4 over ni. Once I have all this cleaned up to be just 3 terms, now I can worry about distributing the 2 through the first set of parentheses, and I can also distribute the 3 through the second set of parentheses. So 2 plus 8 over ni plus 8 over n squared I squared minus 3 minus 6 over ni plus 2. Combine like terms. We get 8 over n squared I plus 2 over ni plus 1. Now, once you have all your high component cleaned up, make sure that you don't forget about the width, right? We still have to worry about this 2 over n. So I'm going to distribute that 2 over n through. Right, so now once we're sitting at these 3 terms, it should become a lot more familiar because now we just have to involve the summations with each of these terms, push out any coefficients, isolate the summation, the parts that require summation formulas, and then we'll bring in the summation formulas. Okay, so next step, I'll do 16 over n cubed summation I squared. 4 over n squared summation I, and then 2 over n summation 1. I boxed off each of these summation terms here because I know that I'm going to replace them with the formulas. So summation I squared turns into n times n plus 1 times 2n plus 1 all over 6. Summation I is just n times n plus 1 over 2, and summation 1 is just n. Now we're just going through our cleanup steps here. Everything is in terms of n. We're within each fraction. I'm just going to look for comparing degrees between numerator and denominator, and then use that information to pull the coefficients in front. Okay, so we talked about a little bit of a shortcut here. This looks like a lot of messiness and time to expand. but really we only care about the first term or the highest exponent with the leading coefficient. So to get to that, just take whatever you see in front, each of these individual terms, just go ahead and multiply them together. So 16 times n times 2n, that gives me 32n cubed. We know there are other terms, but all those other terms will produce a lower degree, which is not going to impact our limit. A denominator 6n cubed. Second term, we get 4n squared plus 4n over 2n squared, and then 2n over n. Within each fraction, we compare degrees, and we're going to see some matching degrees here, so we're just going to take the ratio of the coefficients. 3's match, we just take 32 over 6. Second fraction, the highest degree is 2. The 2's match, we just take 4 over 2. And the third term, degrees match, we just take 2 over 1. Combine those together, combine those terms together, and we get 28 over 3. And the significance of that number is that 28 over 3 indicates the exact area of that region that we're talking about.
Mr. Yang?
Yes.
Will you ever get degrees that aren't matching?
Yeah, let's talk about that. Previous classes were also bringing up that question. So let me point something out here. It's okay if your degree in the denominator is higher than the numerator, because if that's the case, it'll just go to 0, right? Like this fraction here, that goes to 0. So if the degree is higher in the denominator, that's typically not going to be an issue. Although for these problems here, if you have distinct terms that you're separating, we should pretty much always get degrees that are matching. But sometimes there are times when you're going to get degrees that's higher in the numerator, sorry, higher in the denominator than the numerator. This is to a third power, and this is to second power and 1. That's typically going to be okay. Now, the issue that you're going to run into potentially is you may run into the issue where all of a sudden your exponent is higher in the numerator than the denominator. Let's say this is 3 and end up with a 2, and you're like, oh wait, what do I do with this? That is a red flag. That indicates that something didn't go quite right in your process. So your numerator exponent should never be higher than a denominator. Okay? We should never get a 3 up here and a 2 down here. Now, if you see that situation, typically the issue that students run into is they lost track of n somewhere along the way. And the most common place where students lose track of an n value is with the height, with the width. Okay. And the reason why is because we spend so much of our time cleaning up the height component that when we clean up our height component, we think that, okay, we're pretty much done, and we forget to distribute the width. Okay, and if you go through this process without the width, then it's not truly area, right? Area needs the width and the height component. So if you're just working through with the width, with the height, then this is where typically we run into an issue where the exponents are not matching the way we would like. So if you see that situation, go back and make sure that you're actually spending the time to distribute the width through so that your degrees will match up nicely.
Thanks.
Mm-hmm. Okay, any questions with the process? It's a long process, but we were able to get through 2 problems, one from yesterday, and we just finished the second one for practice. Okay, let's go to trapezoids. So this is page 10 in your packet. Now we decided to bring in 4.6 as well because while we're doing rectangles, we might as well just take care of all the geometric shapes that can provide approximations for us. So we're just going to go ahead and cover trapezoids as well. So trapezoid rule is a way for us to approximate the area of a region using areas of trapezoids. The big thing that we're going to see with trapezoids compared to the other rectangles is that it's just naturally going to be a better approximation than inscribed, circumscribed, or midpoint rectangles. The way that trapezoids are shaped is just naturally going to fit the path of the graph a little better than what rectangles can do, assuming that we're using the same number of rectangles and trapezoids. Okay, so let's work our way to that example. As a review, area of trapezoids is 1/2 height times base of 1 plus base of 2. I think typically this is the formula that you're used to seeing if you've seen it in the past. You've seen it where it's the horizontal bases that are parallel to each other. Okay, so that's where 1/2 height times base of 1 plus base of 2 is coming from. Now, this is not the orientation that we're going to be using as we're using trapezoids. We're actually going to be kind of flipping it on its side. So if you imagine pushing this up to its side to make it look like this. So now, because we have a different orientation, we're going to now, instead of calling this height h, we're going to call it base or the width. And then instead of calling the horizontal parallel sides base of 1 and base of 2, if we flip it to the side, then it's the vertical components that are parallel. So we're going to call it h1 and h2. So it'll either look like this with the top sloping up, or it may look like this with the top sloping down. Okay, either way, that's the orientation that we're going to be seeing our trapezoids as. So we're also going to adjust the formula to make it a little bit to match the orientation that we're using. So instead of h over 2, we're going to do b over 2, or how about this? Let's use width instead. I think we're going to use width more often. Width is more descriptive. Width is just that horizontal distance. So width, 1/2 width times height 1 plus height 2. So I'm going to be using this formula for my examples. All right, let's go ahead and try example 1 here. Estimate the area bounded by the function 6x minus x squared and the x-axis using 6 trapezoids. So here we have our curve. We have the x-axis. It's bounded, so we know that there is a starting and ending point created by the intersections between the graph and the x-axis. And then the intersections will provide the a and b values. So let's spend the time to see if we can find those a and b values. We're going to set the function equal to 0. And that will tell us the intersection, which will tell us the a and b values. I can factor an x out. Solve for x. I get x equals 0 and x equals 6. So now we can go through our width formula. Our width is b minus a over n. We want to create widths that are all the same across all the intervals. Our a value is 0. Our b value is 6. And our n value is also 6, right? N is number of intervals, subintervals. Six over 6 is just 1. A nice easy number to apply. So we know we're starting at 0, we're ending at 6. Each of the subinterval values are 1, so we're just going to keep adding 1 until we reach our right endpoint. Now that we have our subintervals established, subinterval values established, Now we're just going to take each of the starting points where our subinterval is, and we're just going to draw vertical lines until we reach our graph. And highlight those points where they intersect. Now let's just connect the dots using diagonal lines. So what we have here, we have a series of trapezoids. I know that the ones at the ends are basically triangles. So, but we can still use trapezoid area to find those triangles, because if one of the heights for the trapezoid is 0, it'll just turn itself into a triangle formula. It would be 1/2 base times height, 1/2 width times height. So I'm going to say 6 trapezoids, even though technically the end shapes are triangles. But what I want you to notice is, look how well these 6 shapes or 6 trapezoids are hugging the graph, or creating a very good approximation of that shaded region, right? We see minimal gaps already with only a few trapezoids drawn. So I just want to kind of make sure that you see visually that trapezoids just have a much better time approximating a region than rectangles do, right? Rectangles, you're going to have much larger gaps either above or below the curve that you're not going to experience with trapezoids. Okay, so that's one big thing I want us to recognize from a visual perspective. All right, so let's see if we can build each of these areas that we have in front of us, and we'll add them together. We know that, again, the area formula we'll be using is 1/2 times width, height 1 plus height 2. Okay, we'll do that for each of the 6 shapes that we see here. A sub 1, we know the width of each subinterval is just 1, so 1/2 times 1. F of 0 plus f of 1. A sub 2. The second shape here, trapezoid, width is 1, but the heights, we're going to attach f of 1 and f of 2 to the curve. Those will represent the heights of my second trapezoid. Third trapezoid. It's going down the line here. Right, I'm going to merge all this together. I'm going to add all this together, but I'm going to see if I can save some writing here. I see all of these terms, they all share a 1/2 and 1, so I can just factor that out once, and then just add all the heights together. Hey, but I'm going to do this part way because I want us to observe what patterns we see with the heights, and maybe that can help us eliminate the amount of writing we have to do here. So imagine adding all the heights together, f of 0 plus f of 1, f of 1 plus f of 2, f of 2 plus f of 3. What patterns do you see with the heights that are being used across all these areas?
The inside heights, there's like 2 of them of each.
Mm-hmm. What about the outside heights?
They're used once.
Okay, why is that?
Because they're endpoints.
They're endpoints. Okay, the endpoints are not shared, right? There's nothing to the left and to the right of those endpoints, but all the middle ones are shared, right? F of 1 is a boundary for the first subinterval, first shape and the second shape. F of 2 represents the height for not only the second trapezoid, but also the third trapezoid. So we could save a little bit of writing space, or the amount of writing we have to write to put down on paper, if we can see that and understand that pattern. So basically the ends are only going to be used once, but all the middle ones are all going to be doubled up. Okay, that can save a little bit of time in terms of having to use a lot of space to add up all the terms. And also we can jump, we don't have to write out all this anymore. We can jump directly to this, right? 1/2 times the width. They're all shared. We can just factor that out and then just start. Once you find each of the subintervals, just start doubling up all the middle ones except the ones at the ends. I do want to point something out here, though, is that you can only do this if the widths are shared. Okay. If we are the ones establishing the width, which is the case here, right? We're the ones doing the width. We're the one establishing each of the individual widths that are the same. So we're never going to run into an issue if we're the ones establishing the width. Okay, we can always factor that width out. However, we're going to see some problems next week where the width is already pre-established for you, where you're going to be given a table of values where every width is potentially different. If every width is potentially different, then we're going to have to find each of the area separately. We're not going to be able to merge them like how we're doing here. But the good news is that if the widths are preset, then typically you're not going to have more than 3, typically just either 3 or 4 at most. Okay, typically only probably just 3. So there's not a whole lot of writing that you have to do, even if it is across multiple area formulas. So if we were to spend the time to find each of those y values into the function, we will just enter that into the calculator one by one. But we're going to just skip that step and just say that that's going to total up to be just 70. All the heights will add up to be 70, divided by 2 is 35. So the area approximation using 6 trapezoids is going to be 35. I do want to point something out here. When you are trying these problems in the textbook for the homework problems, this is 4.6, and 4.6 we would have already established what the integral notation is. And we haven't quite talked about the notation for integrals just yet, but just for we won't get to it until probably later after the quiz. So I just want to show you what this problem would look like if you were to see it in the textbook. Okay, we'll talk a little bit about integral notation, but I just want to point out that if you see a problem from the textbook with 4.6, just know how to gather information if it's in this notation. Know that the expression that you see here is the function you're working with. And then there's a lower number that you see here. That's your lower bound. That's your A value. And then your upper bound is this top number. So if you're able to take this notation and just pull the information, the function, the A value and the B value, then that's enough for you to get started with the problem, right? Oh, and then the problem will tell you what the n is. It could say n equals 4, n equals 5, and so that will be provided for you. So if you have your function, your A and B value and n value, that's all you need to help get started with the problem, right? You can gather the width, build your subinterval, and then start putting into the formula. Okay, any questions with trapezoid rule here? Okay, I do want to spend time reviewing with each of these approximation methods. And also I want us to bring in table of values, but let's do that probably Monday or Tuesday after I get through all the new material. So it will be in your packet that I give you on Monday. But let's move into talking about power rule for integrals. I don't have this in your current packet. If you printed this out, this will be under today's notes on my website under Friday, the 7th. If you didn't get a chance to print this out, then just kind of follow along. I'm just going to go through the formula for power rule, explain it, and then go through some examples. We talked about power rule for derivatives in the first semester, but now we're talking about power rule for integrals the second semester. But they're related, okay? So let's talk about power rule for derivatives and see how that's related for power rule for integrals. Let's say from first semester I gave you f of x equals x squared, and I asked you to find the derivative f prime. Okay, you would tell me the derivative would just be 2x. Okay. And you would use power rule for derivatives. You would take that exponent that's in the original problem, in the original that's showing in the original expression, and you would bring that exponent down in front, right? That n will come down in front, that 2 will come down in front, and then you would subtract 1 from the exponent. So the 2 comes down in front, that becomes 2x, and then you took that exponent, subtracted 1 from it, 2 minus 1 is 1, so we get 2x to the first power. Now, to put those steps for derivative power rule into words, let's think about the operations that were applied through that process. We would bring the exponent down in front, and what operation will we do here? Multiply, right? And then once we took care of that multiplication operation, then we would do n minus 1, which is subtraction. Now let's say we're sitting at 2x as the derivative, but let's say we want to make our way back up to x squared. All right, what operation will we have to do if we wanted to undo these previous operations? All right. Instead of subtracting, we're going to do what? Add, right? Adding is the inverse procedure of subtraction. Instead of multiplying, if we want to undo that multiplying step, we would do what? Divide, right? So that's going to tell us, just want to kind of give an intro as to the power rule for integration. Right? We're going to add and divide instead of subtracting or multiplying and subtracting. So just as a quick example here, if I wanted to bring that 2x back up to x squared back up to x squared, we know we're starting off with 2x to the first power. We're going to add 1 to the exponents. Which gets us 2x squared. But then immediately after that, we're going to divide by that new exponent. Right? That exponent is now divided as well. We took care of 2 operations. We added and we divided. You get the 2's to cancel out, and you're left with x squared. All right, so we're just undoing the process that we did from first semester, and we're going to call that process power rule for integrals. And that's shown in this integration rule here, that n plus 1 indicates that we're adding 1 to the exponent. And then the divided by n plus 1 indicates that we're dividing by that new exponent. Let's talk about notations that you see here in front of you. This is the integral notation that indicates that we're taking the antiderivative. We're undoing the process of derivatives here. This expression that you see here is called the integrand. This is the expression that we're working with. Here's an example of integrand, could be 2x. And then what follows after it is this dx. That dx indicates that, that we're dealing with the independent variable x. Now, this is not the first time that we've seen dx, right? We've seen it from derivatives as well, right? If I gave you y equals 2x squared, you would say y prime or dy dx equals 4x. Right, we've seen that notation before, but we just understood that notation to indicate that we're working with our independent variable that we're working with is x. We're finding the derivative with respect to our independent variable x. Same thing here. This dx indicates that we're taking the antiderivative with respect to our independent variable x. Also, just to kind of point out, this kind of works in nicely with what we know with slope and area, right? Slope is division related, right? Change in y over change in x. But area is rectangle related, width times height. So there's a multiplication component that kind of shows that we're doing the opposite procedure of slope, which is division related. X squared plus c, x squared is the antiderivative, and then the plus c is what we call the constant of integration. Okay? It's going to show up each time we take an indefinite integral. Okay, so let's talk about what this plus c means and why we need it. All right, so back to derivatives here. Consider the below functions. F of x equals x squared plus 5, f of x equals x squared minus 13, and f of x equals x squared plus 126. Now, if I ask you to find the derivative of each of these functions, what would you say? They're all going to be what?
2x.
They're all going to be 2x. So even though these are all different functions, they're all producing the same derivative. All right, we know why, because it's only the x squared that's dictating the derivative. We know the constant will just fall away. Okay? But the big idea here is that we have infinitely many functions that all share the same derivative. But it's infinitely many functions within the certain family of functions. Okay. Basically, since we can add a constant to any of these functions and still result in the same derivative, right? It could be x squared minus 50, and it will still give us 2x. We want to create a situation where we can identify all the families of functions or all the values that all share the same derivative. So that's why we have it in the form of f of x plus c. Okay. That plus c indicates that there's a family of functions that all share the same derivative. So for instance, this is what it would look like if I asked you to find the integral of 2x dx. You would go through this process, add 1 to the exponent, make it 2x squared over 2, and then you would say plus c. So that tells us that we have infinitely many functions under the family of x squared that all share the same derivative of 2x. That's why we need that plus c there. Okay, the process of integration is called anti-differentiation, or taking the indefinite integral. Indefinite integral results in a function. So that's what we'll be working on for a week or so. We're just going to be working with integrals without bounds, basically. Okay. Integrals without bounds will always produce a plus c, function related. Now, definite integral, this is what we're going to get to after next week, are integrals where we have bounds involved. If we have bounds involved, then this will result in a value which will be an area related value or number. Okay, let's just spend the remaining few minutes going over a couple of examples on the back page. So here is power rule that we'll be using. Add 1 to the exponent divided by that new exponent and then plus c. I'll talk about the second rule in a second, in a bit. Now, going back to derivatives, recall that we had conditions for power rule derivatives. Those same power rule conditions for derivatives also apply for integrals as well. So let's revisit those conditions. Any radicals, we want to make sure we rewrite as rational exponents. Okay. Anytime we have variables in the denominator, we have to make sure we push it up to the numerator, right? We can't do power rule if we have variables in the denominator. If we have variables in the denominator that we can't find a way to move up, then we need to explore something else. We're not going to be able to use power rule if the variable can't be pushed to the numerator. And the third, we want to make sure that we expand our expression fully. So what we mean by that is resolve all parentheses. We can't have parentheses with a value outside or exponent impacting the parentheses. We have to find a way to expand it fully. If we're not able to expand it fully, then again, we have to explore other options. We're not going to be able to use power rule. So power rule is going to be the rule that you use the most often, but it also comes with very distinct conditions that need to be met before we can apply them. Okay, let's start off with easier one here. 7x dx. We know the integral of 7x dx. Every condition is good to go. There's no radicals to rewrite. There's no variable to be moved to the numerator. It's already in the numerator, and there's no parentheses. It's already showing as 7x to the first power, so we can just jump into power rule. We add 1 to the exponent and divide by that new exponent. You can rewrite it. You can write it as 7x squared over 2 plus c, or if you want to just get into the habit of not having to stare at a numeric value in the denominator space, you can always rewrite it as 7 over 2 x squared plus c. You can push it out in front as a coefficient. Typically, students like this more. It just doesn't seem as intimidating as looking at a variable, looking at a value below a variable. Okay, I want to do something related here. What if I just ask you for the integral of 7 dx? Okay, so the big idea that I want you to take away with power rule for derivatives versus integrals is that for derivatives, you expect all of your exponents to fall by 1. Right? X cubed becomes 3x squared. Right? 4x to the 4th power becomes 16x to the 3rd power. Every degree is going to fall by 1. With integrals, all of your degree is going to rise by 1. Right? 2 becomes 3, 3 becomes 4, 4 becomes 5. Now 7 has an x, has a variable x to what power?
0.
0. So 7 is going to turn into what?
7x.
That's right, plus c. Right. So every degree is going to rise by 1. So here, this is really x to the 0 power, which will now all of a sudden become x to the 1st power. And that's what this second rule is telling us here. Any constant is going to rise by 1. So 3 will become 3x. 1/2 will become 1/2 x. 10 will become 10x. And if you look at this from a derivative perspective, it should make sense as well, right? Because derivative is just going the opposite direction, right? 7x's derivative is 7, right? So therefore, the integral of 7 must be 7x. And we're just learning how to go backwards here this second semester. All right, another easy example here, integral of 7x cubed. Every condition is met and ready to go. We can go through power rule. 3 is showing, we add 1 to the exponent, we get 7x to the 4th over 4 plus c. We can push that 7/4 out as, or that 4 out as 7/4. Okay, either way is fine, it's just typically I like to encourage students to push coefficients out in front. Okay, one last one here. 2x plus 3x squared minus 5x to the 4th. Every term is set up and ready. There's no issues with radicals. There's no denominator variable. There's no parentheses to worry about. So 2x becomes 2x squared over 2. 3x squared becomes 3x cubed over 3. And 5x to the 4th becomes 5x to the 5th over 5. Now, typically, you can look at this and say, well, every term is going to produce a plus c, so we could say, hey, this is all just plus 3c. Right, but I want to talk about this in a second here. First off, I can clean up a little bit here. I can get x squared plus x cubed minus x to the 5th. Now, c is a constant, okay, but 3 times a constant is still a what? Okay, it's still a constant. So we can kind of just let all of the constant kind of get merged together. We can let that 3 get absorbed into the c, and we don't have to keep track of the number of c's. We just say just plus c. Okay, it's not wrong if you wanted to include a plus 3c, but there's no need to, right? We can just say that, okay, all the constants, let's just let it all get absorbed into one notation, and that we'll just let that plus c handle all the constants, all put together. Okay, and then really quickly, number 4, 3x minus 1 squared. There is an issue with one of the conditions, and that condition is that it's not fully expanded yet. So we can't do power rule, just like with derivatives, if there's an exponent getting in the way. So we need to spend time to FOIL this out, right? So the way we FOIL this out, we write this out twice, expand, 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 get all the parentheses to go away. And once every term is nicely cleaned up with no parentheses in the way, then you can do power rule. 9x cubed over 3, 6x becomes 6x squared over 2, 1 becomes 1x, and then just have to write plus c one time. All right, great. We'll pick up on Monday. Hope you guys have a great weekend. Okay, see you guys Monday.